Okay, today we're going to be talking about lecture 21. So if you don't have that down yet, you can go ahead and get it. Just briefly, if you look at this, you may get panicked suddenly because of everything that is due. Many of these are 10-problem assignments. They're small things. The big thing that maybe you haven't worked on much yet or any yet is the related rates project. That's a test grade. That's due this Thursday. So you need to go ahead and get started on that. You do have a web assign tonight and a web assign Thursday night. Now, I don't mind pushing tonight's web assign off one more day if that's going to help, but it's not going to change what we do in class. We're still going to keep moving forward on that. So would it be of assistance to push that web assign off one night for you? Yeah. Okay. I will push it off one night. That doesn't mean you have to do it tomorrow night. You could go ahead and get it accomplished tonight. It's over stuff we've already talked about, critical points and extreme values. So those of you that have already turned in that homework 20, I've already graded it and given it back to you. It's not a very hard concept, but I will move that web assign 11 to Wednesday, so you'll have a web assign Wednesday and Thursday. Any questions about what's coming up right now? We've got a test scheduled right now for next Wednesday afternoon. Next Wednesday afternoon. It'll be over what we talked about before: critical values, extreme values, roll, MVT, first derivative, second derivative. Those are the things that will be involved in it. We'll talk more about it as it gets closer here. All right, any questions so far? Let's briefly talk about, before we get started with today, let's briefly talk about what we have already talked about. What are critical points? Does anyone remember? Yes, sir.
Points at which the derivative equals probably 0.
Or f prime is undefined. Okay? So it's one of those two things. Now, why are critical points critical? What happens at critical points? Anyone remember? Things change, okay? Can we be a little bit more specific? Okay, the direction of the function changes. And what can occur at those points because the direction of the function changes? That's right. Extreme values. Extreme values. And what do we mean by extreme values? They are either what or what? Highest or lowest points. The most common thing is they're the max or the min. And on the last time that we met, where do max or min occur at? Where? They occur at critical points or where else? Endpoints. Okay? So that's all kind of behind us. And we worked a little bit on finding extreme values in the last assignment. We found the critical points, and then we evaluate the function at the endpoints and the critical points. And that determines, then it's real easy. We look at it, the biggest one is the highest, it's the max, the smallest one's the lowest, that's the min. Well, today we're going to take a little different turn. And I want to start off by asking a relatively simple question and see if we can get some discussion from the class. So read over that question there and give me an answer. Okay. So we've got the yeses and we've got the no. Yes, there's enough evidence. No, there's not enough evidence. Wesley says no, there's not enough evidence. Okay? Chase was nodding his head. What was he nodding to? Yes. Okay. Gabby says yes. Chase says yes. Marty says yes. Uh-oh, you're getting outweighed here, Wesley. Uh-oh, what? Y'all have changed. All right, well, now, with 4 people over there, I find it highly unlikely that anybody's going to go against the norm now for fear of being different. So the real question is, why? Okay, so he went 5 miles in 4 minutes, which is how much of an hour? 4/60 of an hour?
No way you can make it that far. You have to be going at least way above.
Right, so if you do this out, 5 miles in 4/60 of an hour, then you find out that he was going 75 miles per hour. That means that was his average, right? So we can convict him because his average was 75 miles an hour? You don't think you can argue that in court that doesn't mean anything? You didn't see, Mr. West, you didn't see me going 75 miles an hour. How do you know I was going 75 miles an hour? Math. I can use math to get a speeding ticket? Wow. Can I use math to get out of the speeding ticket? Might be the better question. Okay, but does this make intuitive sense to everyone here? And if you think of it, I want you to think of it like a graph, okay? This is his position down here. This is, no. This is time down here. This is his position over here. So to begin with, he was at 0, 0, and then 4 minutes later, he was up here at 5 miles an hour. So this is 4, 5, and that's 0, 4, or let's call it 4/60 because that'll be in units that we make sense of. So what essentially did we just find with this 75 here? This 75, mathematically, what did we find? Five over 4/60. What is that mathematically? If he started here, we found the slope, right? This is essentially the slope between 2 points. Agreed? Between the 0, 0 and the 4/60 5. That's the slope of what he was going there. And that's the average slope there. Now, and it makes sense that if his average in here is 75, that somewhere he had to be going 75. Does that make sense? Somewhere he was probably going less, somewhere he was going more, but average in here, we don't know what this would look like. I mean, he might have been going along like this and then suddenly jumped up. Well, it couldn't have looked exactly like that. He might have been going along real slow and then got real fast and then got real slow. But somewhere in here, he had to be going 75 miles an hour. That's right. Immediately, as soon as you see a car that looks like an officer, you get your foot off the gas. Even if you aren't speeding, you just get your foot off the gas. It's instinct. So the average in there was 70. If the average was 75, he had to be going 75 somewhere in there. Had to be going 75 somewhere in there. Well, what you have just described for me is a theorem that we're about to talk about called Rolle's theorem. And we'll forget about the continuous part here. Rolle's theorem says if F is continuous on AB. All right, now let's stop and talk about what that means. What does it mean for a function to be continuous? Who remembers what it means to be continuous? What does it look like if it's continuous? There's no holes or no jumps, okay? So this means there's no holes or jumps, okay? Jumps. All right. AB are X values there, okay? This is on an interval AB. Interval from A to B. That means if we start over here at A and we end over here at B. Okay? That type of interval. Okay? The next part of it says it's differentiable on AB. Now, first of all, what does differentiable mean? What does it mean to be differentiable? Is that the same thing as continuous? Must not be, since we separated them out. Differentiable means no sharp turns. Okay? It's differentiable and it's no sharp turns. Notice that the AB this time has parentheses around it. What does that mean? How is that different than the square brackets? It doesn't include A and B. So it's only differentiable from as close to A as we can get to as close to B as we can get. So we know that it starts at A, it ends at B, and it has to be smooth in there. And one other criteria for Rolle's theorem says f of A equals f of B. What does that mean? Function value at A is the same as the function value at B. Okay, so before we even read about the rest of it there, okay, let's take what we know. We know the A value, A and B or X values. We know that the function value at B has to be equal to the function value at A. We know the function has to be continuous, and the function value has to be differentiable. So in your mind, draw some examples of what that could look like. We don't know what it looks like, but we know. But just think in your mind what it could look like. It could be very bland. It'd be a straight line. It could be a little bit more exciting and do something like that. Or it could go up like that. It could do something really funky and do something like that. You see, there's endless possibilities of what it could look like. What do we know it doesn't look like? It doesn't look jagged. It's not going to do something like this. Okay? It's not going to do something like that. How do we know it doesn't do that? That's right. We can't differentiate this. We can't find the derivative at these corners here. So we know it's not differentiable. Okay? We also know that it's not going to do this. Something like that. Because that's not continuous. So the solid lines is things it could look like. The dashed lines it couldn't be. Okay? So I'm going to try to take the dashed lines back off. And then let's read the rest of it. Ooh. All right? What does it say? It says, then there exists at least one C on AB. Now, that means there has to be an X value between A and B. There has to be a number between A and B such that, what does that say? The derivative is 0. That's what we know. There has to be a point in there somewhere such that the derivative equals 0. So look at this blue, red, and black line there and see if you agree that the derivative has to be 0 somewhere. Yes, ma'am.
Shut down, fine.
Uh-huh.
And it might start today. Danny said he'd pursue it. You could tell he knows nothing about it.
Mm-hmm.
Do you have any clues? We've plugged it in and I've docked it.
Is that where I plug it in at? Somebody go up there and point out on the black line where it has to be equal to 0 for us. On the black line, somebody come up here and somebody come up here and just highlight where it has to be, where the derivative is 0. Can you find some points? The board is workable. Go for it, sir. On the black line. Where's the derivative equal to 0? Okay. Now the black line is, the green line has nothing to do with it there.
Okay.
Where the derivative of the black line equals 0. My suggestion is let's just let it sit here and power for a little bit. It could be that it hasn't been getting power over the last few days for some unknown reason, and it's just graveyard dead. So yeah, so let's let it sit here for 45 minutes and come back.
I actually have to do someplace at 9.
Okay.
I may come by here, may not.
All right. So where if I ask you with the black line, where's the derivative equal 0? Very good. Okay. There's 3 places. There's actually 2 more with the black one that you could circle there. All right. Good. How many places do you see with the red that it would be? 1. What about with the blue? How many do you see? All of them, okay? Describe all those points. No, the derivative is equal to 0 at all those points. Tell me something else about them. Okay. They're all maxes or mins. Very good. Very good. Y'all are getting closer. The derivative is 0. They're all maxes and mins. They are, how could you describe them? What word could you use to describe them? What? Yes. All of these are critical points, okay? Okay? So, Rolle's theorem says that if we've got a continuous function and we can find one place where the derivative, if we can find 2 places where we know the function is equal, okay, so get that in your mind. You've got 2 places where you know the function value is the same thing. There has to be a critical point between them. Has to be. As long as the function is continuous and differentiable. Now, we don't know what it is. We may not be able to find it, but there has to be one in there, okay? That's what Rolle's theorem says for us, okay? Now, I know you don't have a complete understanding of that, but I have a question for you. Does Rolle's theorem apply to what we talked about to begin with? Does Rolle's theorem apply? I cannot. Does Rolle's theorem apply to this? We know the car didn't stop.
Well, we know it didn't stop if it slowed down. It does, right?
We don't know it necessarily applied because it might have stopped in there. Were the endpoints the same? The endpoints weren't the same. So really, Rolle's theorem wouldn't necessarily apply here. But we have something that we call a corollary to Rolle's theorem that does apply. Now, I want you to read the mean value theorem. Tell me what's different about the mean value theorem and Rolle's theorem. Right. The only difference between them is, the only difference between the if part is that the function values are not the same. Okay? And this is really what we used in order to solve that first question a while ago. Because we knew that the function values weren't the same. He started at one place, and 5 miles later he was somewhere. But the mean value theorem says that if the function values aren't the same, so let's draw that picture. We've already done this kind of with the other one. Let's say we start here at A. We've got a function value. We stop at B. We've got a different function value. Again, if we know the function's continuous and differentiable, it could do all kinds of things in here. It could just go straight up. It could curve down below or up above. It could go up and come down. But irregardless of what it does, there has to be a point so that this is true. F prime of C is F of B minus F of A over B minus A. Now, students often get confused with that right there. But now really take a look at the right-hand side. F of B minus F of A over B minus A. What is that saying to find? F of B, saying take the function value at B minus the function value at A over B minus A. What is that calculating, that right-hand side? The slope. This is finding the slope of a line, is all it's doing. And that's what we talked about in the first question is, if we can find the slope of that line, then there has to be somewhere that the derivative is equal to the slope of that line. Okay? And that just makes very intuitive sense to us, okay? Now, if we go back to the original problem, we can't guarantee that that car didn't stop, that truck didn't stop somewhere in those 5 minutes, can we? 4 minutes, whatever it was. So he could have stopped in there. But if he stopped, what would that do to his speed? What would that mean about his average speed and his instantaneous speed? If he stopped somewhere, would it make his if he stopped somewhere during that 4 minutes, what does that mean he had to do? He would have gone faster. That's right. He would have had to go even faster in there somewhere. Okay? So we could use it, even though the mean value theorem wouldn't exactly apply. We could still utilize it here. But these are the two big pictures that you need to get, roll and MVT. Okay? Really? My opinion, if you memorize MVT, you've got rolls anyway. Because what happens if the endpoints are equal to each other? What happens over here? Then it's 0 over something, so it's equal to 0, right? So as long as you know the MVT, you can solve any problems that might need to use MVT or Rolle's theorem. Big thing you need to remember with all of these is that F has to be continuous. That's the first thing. F has to be differentiable. That's the second thing. Now, how do you look at a function and determine if it's differentiable? When do we have to worry about something being not differentiable? Piecewise. Piecewise? It involves radicals and denominators and LNs. Okay? Those are your 4 things that you have to worry about. Remember, that's when we had to worry about continuity. So anything that you worried about continuity, that's when you worry about continuous and differentiable. So now I know you don't feel super comfortable, but let's look at a problem here and see how this actually applies. Find the x-intercepts of the following function and show that the derivative equals 0 at some point between them. Okay? Find the x-intercepts. What does that mean? Find the zeros. How do we find zeros? And how did you find that? All right. That's right. You're going to set this equal to 0. You can factor it. So that means x is 2 and x is 4. Right? So now think about what we know graphically suddenly. We know that at 2, this function crosses the x-axis. We know that at 4, this function crosses the x-axis.
No, there has to be a place where it's 0.
Right. And how do we know that there has to be a place where the derivative equals 0? What are we using, rolls or MVT?
Well, it has to go back.
Okay. Okay. We know we're using Rolle's theorem, okay? That's named after the man that first penned it, okay? Rolle's theorem says that because f of a equals f of b, the function is continuous, the function is differentiable, you've got all three pieces to it, therefore the derivative has to equal somewhere, 0. Not only does it have to equal 0, it has to equal 0 somewhere between 2 and 4. Now, how could we find out where the derivative equals 0?
We could find the highest or lowest value.
And how would we do that?
We would set the derivative equal to 0.
Very good. Find the derivative, which is 2x minus 6. Set it equal to 0. And we get x equals 3. So now we know that the function has a point where the derivative equals 0 by Rolle's. We know what that point is because we took the derivative and set it equal to 0. When in doubt, find the derivative and set it equal to 0 because that's what you're going to do 75% of the time with problems. Find the derivative, set it equal to 0. Any questions about that? It has to be equal to 0 somewhere. We said that by Rolle's theorem. We found out what it is by finding the derivative, set it equal to 0. Not a complicated process necessarily. Now, find the values of c on the interval -3 to 3 such that the derivative equals 0. So how are we going to accomplish this with this particular function? Boom. Take the derivative, set it equal to 0. So if we take the derivative of that, we get 4x cubed minus 6x. Set that equal to 0. How many answers do we expect to get? 3, yes. Let's take out a 2x, and we get 2x squared minus 3 equals 0. So then we get x equals 0. 2x squared equals 3. X squared is 3/2. So x is plus or minus the square root of 3/2. Okay? So, are all three of those on the interval -3 to 3? Are all three of those between -3 and 3? They are. Okay? Do you think you could kind of draw out what this... Well, let's don't talk about that yet. We'll talk about drawing it later. But suddenly we found all three. Did we use Rolle's theorem or MVT?
Rolle's.
How do we know we use Rolle's? We set the derivative equal to 0, okay? Now, we made a kind of an assumption here. If I put -3 in here, strictly to use Rolle's, we need to put -3 in there and figure out that that's 81 minus 27. And f of 3 is 81 minus 27. So since these are equal, we can use Rolle's, okay? Strictly speaking, we'd have to do that to show that we could use Rolle's theorem. But in actuality, as long as you take the derivative, set it equal to 0, you find your 3 points, and you're good to go. In this case, it was 3 points. Now, when you look at this next problem, given f of x equals 5 minus 4 over x, find all values of c on the open interval 1 to 4 such that that's true. That's right. This is MVT. As soon as you see this, you can say that it's MVT. Bless you. All right? Now, is the function continuous everywhere? No. Why not? Right. So we can't put 0 in this function, so the function is not continuous everywhere. Is that a problem for us to solve this problem? Very good. It's a problem if we've got a different interval maybe. But look at the interval we've got from 1 to 4. 0 is not in that interval, so we can say that the function is continuous from 1 to 4. It is differentiable from 1 to 4. So we just need to solve that problem over there. F prime of C equals f of 4 minus f of 1 over 4 minus 1. Do you have the capabilities to solve that problem? What does it mean to do?
Well, that's the slope of the equation.
Mm-hmm.
So there's always one point where the slope of the equation is one point.
Yes. We know there has to be one by MVT. There has to be a point. So how do we find that point?
You set the derivative equal to this.
Set the derivative equal to this number. So if we take the derivative of this, we get minus 1. That's 4x to the negative 1. So that'll be minus negative 4x to the negative 2. That's what I get over here. Let's clean that up. Make it 4 over c squared, because we're f prime at c, equals f of 4, what did you say it is?
I said that the entire thing, if you were like, plug it at the end was 1.
Okay, because when I plug 4 in here, I get 5 minus 4, which is 1.
And then you get 5 minus 1.
5 minus 1, which is 4. That's what I said.
The same part, you get 5 minus 4, which is 1.
Uh-huh.
Over 4 minus 1, so 1.
1. Okay, so we've got 4 over c squared equals 1. So what do we get for c?
Where do you get 4? How do you get 4?
Where do we get this?
C equals 2.
Okay, taking the derivative of this function. F of x equals 5 minus 4 over x, which is 5 minus 4x to the negative 1. 5 is going to go away. If I take that derivative, that makes it positive 4x to the negative 2. So if we solve that out, we get 4 over c squared equals 1, which means c squared equals 4. So c is plus or minus 2. You certainly can.
So why would you go for x to c?
Wait, where did you get 4?
I mean, I get the math, but why did you change?
Why did I change to c? Simply because it said f prime of c there. It would be fine. It wouldn't change anything if you left it at x is there. Where'd what 4 come from?
4 over c squared.
Where did this come? This is the derivative right here. But notice in the original problem it said f prime of c, so I just put c in place of it. Okay. Negative 2 is not an answer, people.
Just 2.
Just 2. Why isn't negative 2 an answer?
Because it's not outside the
That's right. All we're looking for is the c on the open interval from 1 to 4. So our only solution here is c equals 2. The answer to the algebraic equation c squared equals 4 is 2 answers, but the answer to our question is only the number 2, because it has to be on the interval there. Anything challenging that we've done here today? Big things to remember. Rolls and MVT, both of them, has to be continuous, has to be differentiable, and if you do that, either the derivative is 0. If you're talking about the derivative equals 0, which theorem are you using? Rolls or MVT? Rolls. I'll remember that by Rolls has a 0 in it, R-O. Okay? MVT means a mean value. That means that they're not equal to each other, okay? You have some time now to work on any of the tasks that you have in front of you.